Hi everyone. So in this video, we're going to talk about sequences. It's pretty straightforward. A sequence is just a set of numbers with a particular order or pattern that emerges. And each number in a sequence is called a term. So sequences are made up of multiple terms. There can be a finite number of terms, like this one, 1, 2, 3, 4, 5. This is a sequence that has a beginning and an end. Or it could be a sequence with an infinite number of terms. Like the whole numbers 0, 1, 2, 3, 4, 5, 6, 7, and they continue forever and ever with no end. So that's an infinite sequence. There's some notation related to these sequences. The first term in any sequence is denoted by A with a subscript 1. So we denote every term in a sequence with the letter A, and then the little subscript returns to where in the order it shows up. Each subsequent term is then denoted by adding 1 to the subscript, so it'd be n plus 1, where n plus 1 is the term number in that sequence. So for example, given the sequence 2, 5, 8, 11, 14, the first term would be 2, a sub 1. A sub 5 would be the fifth term, so here's term 1, term 2, term 3, term 4, term 5 would be 14. Then if I want term 8, I'm going to have to kind of try to infer what kind of pattern is going on here. So if I notice, it seems that I'm adding 3 each time. 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 3 is 11, 11 plus 3 is 14. So if I want to go to 8, I'm going to have to add on. So the sixth term I'd expect to be 17, the seventh term 20, the eighth term 23. So a sub 8 I'd expect to be 23. And then if I want 14, so it's 8, so then the ninth term would be 26, the 10th term would be 29, the 11th term would be 32, 35, 38, and finally 41 by the time I get to the 14th term. So now that's obviously very cumbersome to have to count up by 3 every time. So we're going to apply some mathematical reasoning to try to exploit these patterns and help us figure out long-term behavior of sequences a little bit more precisely. So I'm going to scroll down just a bit. Sequences can also be thought of as functions, where each term is paired with a particular number in that order. The domain would be the set of term numbers, just where does it show up in the order, first term, second term, third term, and so on. And the range is the output, or the actual term I observe. So these are the term values. Okay. In an infinite set, the domain turns out to be the set of all natural numbers. You'll remember that a natural number is the counting numbers. It's 1, 2, 3, 4, up through infinity. I can always continuously count up by one more number. Great. So that's the basic definitions. There is one other kind of sequence that you should be familiar with, and it is a recursive sequence. A recursive sequence is just a sequence whose terms can't be explicitly defined on their own and are instead defined in terms of previous terms in the sequence. A great example is the Fibonacci sequence. So in this sequence, the Fibonacci sequence, it starts with 0, and it has 1, then it has 1 again. And after the first two terms being 0 and 1, every subsequent term is defined as the sum of the previous two terms. What do I mean? Well, in this particular instance, 1 is obtained as adding 0 and 1 together. If I add these two terms, I get 1. If I add 1 and 1, I get 2. If I add 1 and 2, I get 3. If I add 2 and 3, I get 5. If I add 3 and 5, I get 8. If I add 5 and 8, I get 13, and so on, to generate all the terms in the sequence. This is what we call recursive, because I can't define the term explicitly itself. I have to define it in terms of using only the previously generated terms. Okay, so here's a couple of examples that we can look at. I want to give the first 5 terms of each sequence. So I'm going to do one with you, and then I'm going to have you do one on your own. So here the first term is 25, and each subsequent term is defined as the previous term minus 7 for every value bigger than 2. So if I was to write out the first 5 terms of the sequence, the first term is very, very generously given to me as 25. And then according to this formula, if I want term number 2, so I'll write here A2, that would equal A2 minus 1, which is A1 minus 7. But A1 I already have is 25. 25 minus 7 will give me 18. Great. We'll say I want A3. Well, A3 would equal A3 minus 1, which is A2 minus 1. So A3 is just the second term, which is 18. Sorry, minus 7. I don't know why I wrote 1. 18 minus 7 is 11. And I can continue to exploit this recursive formula, looking at the next term and subtracting 7 every time to get 4 and negative 3 as my first 5 terms of this sequence. So I would like you to take a moment, pause this video, and see if you can use the recursive formula given in the next question to generate the sequence. Great. So hopefully you came up with this, -2, -5, -14, and so on. So using a given formula to generate a sequence is great for getting to know sequences pretty well, but we actually really want to do it the other way. I want to be able to take a given sequence and write the formula. Here are a couple of other practice questions if you'd like to some extra practice, 3 and 4, but I'm going to skip right down to question 5 here. Write a recursive formula for this sequence and find a sub 8. So I want to find a formula for the 8th term and then compute that 8th term, a way to kind of figure out what the next terms in the sequence are. So as I'm looking at this, it's helpful to kind of see if I notice any patterns. And it looks like from 9 to 13, 13 to 17, it looks like each term I'm adding 4 on. So I'd expect the next term to be 29, after that 33 and 37. So that's what I expect my terms to be. So if I'm setting up a formula for this, I can do that by first stating where the sequence starts, which is at 9, and then defining the pattern I noticed. I noticed that we were adding 4 every time. So that means that each subsequent term is equal to the previous term plus 4 for every term after the first term. And if I continue that pattern out until I get to the 8th term, I can find that A sub 8 is 37. So take a moment again, pause this video, see if you can figure out what pattern exists for question 6, and then write that pattern in. I'll also reveal the answers to question 3 and 4 if you want to give those a try. So go ahead and pause this video now. All right, so here are the solutions to each of those problems. Question 6 actually depends on 2 previous terms, where each term is equal to double the sum of the previous 2. For example, 1 plus 3 is 4, doubled is 8. 3 plus 8 is 11, doubled is 22. 8 plus 22 is 30, doubled is 60. So the way I would describe this sequence is I'd add the 2 previous terms, so the n minus 1 and n minus 2, the 2 terms preceding the third, and double that value. This is true for every term bigger than 3. And if we use that same pattern to extrapolate out, I get that the 8th term is 1,224. Okay, so those are recursive formulas. What about explicit formulas? So an explicit formula is just a rule for the nth term which is defined as a function of n. So given the nth term, I can just plug in n. It does not depend on any of the previous terms. For example, a sub n is 5n plus 1. If I want to write out the first terms of the sequence, I'd plug in 1, 2, 3, 4, and 5 for n. Computing that, I'd get 5 times 1 plus 1 is 6, 5 times 2 is 10 plus 1 is 11, 5 times 3 is 15 plus 1 is 16, and so on to generate the first 5 terms of the sequence. Use the same patterning to do question 8. If you do so, you should get plugging in 1, 1 minus 1 is 0, so I get 1, then 2 minus 1 is 1, 2 minus 3, and so on, and I can generate each of the terms in this explicit sequence. There are 4 other practice questions if you'd like to give that a try. I'm going to reveal the answers to those so that you get a sense of what the solutions would be to check your work in just a second. But I'm going to slide right on down here to look at question 13, which is writing an explicit formula for the sequence given. Now, I'll give you a quick tip for helping to come up with an explicit formula for a given sequence. And something that can be helpful is if you write out the sequence number, or what term, the term number, that each of these terms corresponds to, and see how could I possibly get a formula in terms of this value, the term number, to get these values, the term value. So it looks like if I just square the term number, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, that should give me a formula to get any term in the sequence. So that's how I would define my explicit formula. It's just the term number squared. And if I wanted the 25th term, I could just plug 25 in and square it, and I get 625. Let's take a look at the second one, or 14 rather, because that one's a little bit trickier. It seems like if I write the term numbers out underneath, 1, 2, 3, 4, 5, I don't really see a explicit relationship jumping out to me. So something else that can be helpful is looking at how, or try starting with some recursive idea. Well, from 9 to 11, I am adding 2. From 11 to 13, I'm adding 2. From 13 to 15, I'm adding 2. And from 15 to 17, I'm adding 2. So it looks like each term is the previous term plus 2. So I'm able to get a recursive formula pretty easily here. Well, if that's true, then let me just sub in the first term and see how I can write out each of the terms from there. The first term is 9, then the second term is 9 plus 2, and then the next term is 9 plus 2 twice. The next term is 9 plus 2 3 times. The fifth term is 9 plus 3 4 times. So if I try to generalize that, I could take 9 and add to that 2 times, it seems like 1 less than the term number. Here's 2 times 1, here is 2 times 2, here is 2 times 3, here's 2 times 4. So it looks like if I did times n minus 1, that should give me n. And I can simplify that a little bit. If I distribute that 2, 2 times n is 2n, and 2 times negative 1 is minus 2, plus 9 would be plus 7. So any term in this sequence I would expect to be written as 2n plus 7, and if I double check my reasoning, 2n plus 7, once I have that explicit formula, I could plug in 25 and I can get that term. Okie dokie. So that's the general introduction to the sequences. If you'd like some extra practice, here are the solutions to these sequence formulas. When we come back to class together, we're going to look at these examples and see what are some tricks and tips that we can use to help us generate sequences more efficiently. All right, I'll see you all then. Take care.